Forgive me for the terrible meme. This was recorded an entire 2 months ago, back when I was young and petulant. I actually thought this was funny, but the point was to show you to use a breadboard. It helps with your organization and you can just store things for later. Use a breadboard. Let's go. So I have a breadboard hooked up to a battery here, and it's obviously a bit too overpowered. And if I was to power this LED with that, it would burn it off. So I need a resistor. I've taken this and measured it out to be a 330 ohm resistor, but you can also tell by the bands. And if I place it this way, we get this switched on. So now I have a switch here that looks maybe like a bridge. It seems like maybe it connects the left to the right, but it actually connects these two sides together. And I'll use that to switch this on or off. And now I can switch it off, on, and off. And this is a typical light switch. It's called a buffer because it maps directly to the input you give it to. So if I switch this on, the light goes on. Anyway. If I switch it off, it goes off. I can just draw a table here. And this is its symbol. It's called a buffer. And when we switch it off, it stays off, and switch it on, it stays on. This is directly mapped. But I'm going to show you something called a short circuit. So if I decide to place this in a way that if I decide to place this here in a way that connecting the switch creates an intentional short circuit, the electrons always follow the path of least resistance. So in this circuit, anytime I switch this, if I switch this switch on, it cuts off the connection to the LED because it's connecting this directly back to the battery. And so we have the situation and we have the opposite here, where if I press the switch, the light goes off, and if I leave it off, the light goes on. And this would be useful for, let's say, a solar street lamp, where you'd want lights to go on when it's dark and the solar panels aren't generating any electricity, and you'd want it to go off when it's daytime and the panels are generating electricity. So in this case, it's the opposite. When it's switched off, it goes on, and when we switch it on, it goes off. And this is called the inverse buffer or the inverter. But you might think, well, those solar panels don't have switches, and the solar panel street lamps don't have switches, and they pretty much work automatically. That's because they use electrically controlled switches like this, called transistors. So this basically works as a switch, but instead of a button, power going into this middle line connects these two lines together. So let's use that and try the buffer again. So we have a circuit connected, but instead of a button this time, yeah, if it gets power to that third part, it goes on, and if there is no power, it stays off. So let's move on to the next thing, which this time is something really interesting. Something really interesting. So if I place two switches like this together in I place two switches in series, that is right on the same line. Let me try this. Yeah. And this switch has to turn on to connect us to this switch, which also has to turn on to connect us to the LED. So here we have a situation where even if I press one of these switches, the LED does not turn on until I have both of them pressed. Right? So we call this input A. If both input A and B, and this is input B, if both input A and B are off, the LED stays off. If A is on and B is off, LED still stays off. And then if A is off and B is on, it still stays off. But when A and B are both switched on, we get the LED on. And this is an AND gate. Let's just draw the symbol here. It takes two inputs into the symbol, and AND gate input A, input B. As I said, when both are off, the LED stays off. When one is on, the other is off, LED stays off. When input A is off and input B is on, LED still stays off. And if both are on, as we see here, it goes on, and that's the AND gate. But just as we did for the buffer, we can also make the inverse of an AND gate, which gives us the opposite of these results. So obviously this would be the symbol, and this is a NAND gate, the opposite of an AND gate. And the way we do that, just like we did that before. First, let me bring this together, bring this a bit closer, so it's tighter. So instead of powering this LED directly, what I'll do is I'll split this into two positions. Right, one that would go right here, and that would require us to, okay, those are, maybe I didn't think that through. These are too close together. so it still works. But the reason I added this gap here is to make sure I split this into two. So I'll have another so instead I'll have another line in parallel, and instead of powering the LED with, I think this should be a longer line. Let's try yellow because it's visible. So instead of powering this LED with through the switch, we power it through this line that is in parallel to the AND gate. And every time the AND gate is switched on, it would short circuit this LED circuit and give us the opposite of that, just the same way our NOT gate works. So this is a NOT AND gate, meaning that it stays on when both switches input A and B are off. When one is switched on, it still stays off. But when both are switched on, okay, that should go off. Let me figure out why it isn't working. Okay, this circuit wasn't complete. Right, so it's not short circuiting. So now this switch should short circuit this light. When both are switched on, then the LED goes off. So LED on when both input A and B are off. When one is on, still off. And when so it's the opposite of a NAND gate, and you'd see that here. So I fill the. Let's have a look at that. We have input A again. Input B. And out as usual. So when both are off, it stays on. When one is on, it still stays on. And the other is on, it still stays on. And then we have both pressed, both switched on. It finally switches off. So you can see that's the exact opposite of what we got the last time, because we added a buffer here and made it a NAND gate. And before I point out what is obvious on this paper, let's move on to another one. I think I'll just power this off for now. What happens if we pair switches up in parallel instead? Now, what I mean by parallel is what happens is if instead of putting these switches in line, I have it so that either of them going on see this with this. Actually, I shouldn't use this. I should use the resistor because we're trying to power an LED. So the way this is set up is so if either of this is switched on, we should get power to the LED. And I have one right here. So okay, so they're both off. And if I switch one on, it switches on the LED. Switch the other on, it switches on the LED. And both switch on the LED. And that's an OR gate. This one is always tricky to draw. And they boot off as we have on the screen. Off. It stays off. When one of them is switched on, LED goes on, and the other is switched on instead. LED also goes on, and both are on. Yeah, so this is obviously different from the AND gate, but flipped, not the inverse, just like flipped upside down, I guess. And I do not want to waste time, so we know that the opposite of an OR gate, it's called the NOT OR, would give us similar inverse results. So let's not go there. We'll just write there. So which results should be opposite of this, which means 1, 0, 0. And that would be because we put a buffer on an OR gate. That is, we make an intentional short circuit OR gate for the line, I guess. That's the opposite. Yeah, so that's, shouldn't bother about the NOT OR. So I want you to notice something between the AND gate and the OR gate. It's almost as if the AND gate is some multiplication. It gives us these. Okay? Because 0 times 0 is 0, 1 times 0, and then 1 times 1 is 1. It's almost like we could do math with this. And for the OR gate, it's addition, except for this pesky one here, because 1 plus 1 in binary is not 1. Well, neither is it in base 10. But 1 plus 1 should be 0, and then you carry 1 around. So how do we get this OR gate to properly give us like a 0 here. So if you notice, as I explained, the AND gate is multiplication. We're sure of that. And if you notice, the results, that's the output from an OR gate, 0, 1, 1, if multiplied by the outputs from a NAND gate, a not AND gate, if you multiply this times 1, you get a 0. Multiply 1 times 1, get 1. 1 times 1, get 1. And 1 times 0, you also get a 0. So that gives us, that's exactly what we want, because a 1 plus 0 and a 0 plus 1 is 1. But a 1 plus 1 should give us a 0, even though we should have something to carry over. So this gate is actually called an XOR. It's called an XOR, and it is the foundation of our civilization. So an XOR, did I say in this should be, okay, mistake. This should be taken in a not AND gate and an OR gate, right? If you take an output from that, and that would be 1, 1, 1, 0. And 0, 1, 1, 1, right? The reason we want this is if, let's say we were adding 3 in binary to 1. We're adding 3 to 1. 1 plus 1 should give us 0, and we carry 1 over. Now, we'd worry about this carry later, but the point is we want to get this in, we want to get our 0 in a case where we have 2 1 inputs, and the inputs to this, come on, NAND gate, will be, yeah, the same inputs as usual. 0, 0, 1, 0, 0, 1, 1, 1. So we want the addition of these to give us 0. That's why we had to get to the XOR. And that's the only way we'd get this properly calculated. And this is a 4. But forget about the math. Let's get back to the circuit. The point is we have to get a NAND gate and an XOR gate. Remember, it's AND is sort of the multiplication. It looks like these are being multiplied. So this would be an AND gate over not AND and an OR gate to get us an XOR, which is